looked at net change in area. We talked about items being removed and added back. We talked about rates of change. And we talked specifically about how derivatives and integration relate to one another in terms of those changes. So what we're going to do today is continue to look at that concept and that idea that integration is truly area under a curve, and we're going to try to bring that idea of area into connection with this. So let's review how the concept of area relates to calculus. If you go way back when, the very, very first thing we did in calculus when we went from derivatives to antiderivatives was what? Okay, and then like what process did we use? We used Riemann sums and then yep, and the trap rule. So way back when, we made a bunch of rectangles and we added them together. So we summed up all those areas under the curve. And we said that the area was actually a limit and that limit was actually an integral. So let's go back and reiterate what that limit and integral were. So the very first concepts we talked about with area in integration was that you had the limit as n, where n represented the number of subintervals, was approaching what? What did we try to do to that n? Yeah, we wanted to make it infinite, right? So I'm going to say, okay, we have an infinite number of subintervals, meaning we have a million, trillion, billion tiny little rectangles underneath there, and we wanted to sum them all together. So we summed up all those little rectangles, and we went from one rectangle to a bunch of rectangles. And then that function was represented by a height and a width. So what did we call the height? Where did we represent the height, more or less? Yeah, it was f of c, right? It was f at whatever value we were on the function. So we had f of c, and we always put like the little sub k because c could move infinitely with k moving. And then the width of that rectangle was, so there was our limit. So we said that the area was actually a limit, but then we said that that limit is actually an integral. And we moved away from the limit notation and we moved into integral notation. So this, if we were finding the area of this graph, would have gone from A to B. And then we still have our f of c, right, or f of x, depending on how you want to label it. And then instead of the triangle, the x, we turned it to a dx. So again, this is where we've come from. This is what we've done. We started with a limit, we moved to an integral. Now, this method worked, and it only worked when we were bounding the curve we looked at with the x-axis. So if you think about all the integrals and all the areas we've talked about so far, all of our rectangles have been bounded by the x-axis. So even if that curve went below the x-axis and looked something like this, we still said, okay, the area was this region in here, right? So even when we looked at a second graph and that graph was below, we just said, okay, it has a negative area because it's below the x-axis, but we still were talking about the curve to the x-axis. What's going to happen today is we are no longer going to look at a singular curve and the x-axis. We have to expand our areas to incorporate larger curves and larger spaces, or spaces that are up higher and bounded by secondary functions. So what I want to do is expand that idea to a different type of function. So now I have curve F and I have curve G. And I want to find this shaded region within here. So my lower rectangle I drew, but it doesn't erase whenever I draw it with boxes. So the idea is that before I would have just had curve F and I'd have found the shaded region all the way through, right? So it would have incorporated this space from here to here. So before it would have said, oh, let's find the integral from A to B of curve F. Or it could have found the integral from A to B of curve G, but again, it would have found this region down here, not this. So what I want you to do is draw a rectangular strip, like I had on my graph, between the two graphs. I draw a rectangular strip in the middle of my two curves. What's the height and width of this rectangular strip? So if the strip went all the way down to here, what would the height of that strip be? It would be. So like if that strip went all the way down, you'd say, oh, it's the height of F. But now, because it's bounded by a lower curve, the height of this rectangle is the top curve minus the bottom curve. So we'll say that H is F of X at some point minus G of X at that same point. So it has to be like how you see. It doesn't matter if you use C or X. It's just saying that, okay, whatever value I plug in, I want this point here to be the same as that point there. So if I pick my height in terms of X, then my width also has to be in terms of X. So the width, again, we don't really specify. Your triangle, or rather your rectangle, might be wider than my rectangle. And his rectangle might be thinner than my rectangle. So that's where, again, we use that idea that width is set to delta x. It's determined by the width of the rectangle you constructed. So we just call it delta x. That's exactly what we're going to do. So we're going to keep that concept in mind that it's the top minus the bottom. The height is truly in this case represented by the top curve minus the bottom curve. So the second question posed to you is, would the height and width of the rectangle strip be different if I drew it in a different place? So if I went and drew a second rectangular strip here, would I represent that in any different way? No, because it's still f of x at whatever this is, minus g of x at whatever this is, and my rectangle's width is still delta x. So the answer is no. But no matter where I drew it, it will always be the same two functions in width. So no matter where you draw it, the height and the width are predetermined by f and g and delta x. So it brings us to the question, how do I find the area between the curves? Well, the area is approximately the sum of all these rectangles. So again, we can write it as a sum, like a Riemann sum. So if we wrote it as the sum, it's the sum of all those rectangles from f of x sub k minus g of x sub k. So there's my heights, times all my widths. And again, k would be 1 to n. So it's the sum of all the heights times all the widths. How can I get closer to the actual area between the curves? So how do we always get closer to the actual area? Instead of doing Riemann sums, instead of doing lots and lots of rectangles, yep, we're going to use integrals. And what do integrals do? Integrals increase the number of rectangles infinitely. So we'll apply the idea of putting a limit on that, which is going to turn this into an integral from a to b of f of x minus g of x dx. So in general, we can say that the area of a region between two curves, if f and g are continuous on a to b and g of x is always less than f of x. And this statement right here is quite important, that the g of x is always less than the f of x. For all x values in a sub b, then the area of the region bounded by the graphs of f and g and the vertical lines x equals a and x equals b will be given by the integral from a to b of f of x minus g of x dx, where f of x is the top and g of x is the bottom. So when we talk about the vertical lines x equals a and x equals b, I'll show you graphically on the next example what those vertical lines they're talking about being bounded by. So let's look at the example, but this time you have to graph it. They don't give you the graph. You have to figure out, okay, where's f, where's g? It's just a bunch of functions and bounds. So we have to analyze and interpret all of this data. So we have the function y equals x squared plus 2. So this graph has a lot of boxes. Treat each box like a half. So instead of treating it like a 1, so they're tiny, treat each box like a half. So that means that 1 is actually going to be at the second. 2 is actually going to be at 4. 3 is actually going to be at 6, 8, and 10. Okay, so what I'm going to do is I'm going to put each graph kind of in a different shade to help you see more easily. So I'm going to treat y equals x squared plus 2 as a red curve. So when I graph it, I'm going to graph it in red. The x squared tells me that it's a parabola. The plus 2 tells me that it's shifted up 2 units. So that means that my vertex is starting at 0, 2. So that means instead of having the point 1, 1, I'm going to have the point 1, 3. And negative 1, 3 as well. And again, instead of having the point 2, 4, I'll have the point 2, 6. And then my second line is y equals negative x. So I'm going to put this line in blue. This is a straight line that goes through 0, 0 and is going down by units 1 over 1. Okay? And then you're given this bit of information here, that x equals 0 and x equals 1. Those are those vertical lines that was talking about. That's the x equals a and x equals b. So a is kind of like 0, and b is kind of like your 1. Because x equals are vertical lines, so if x equals 0, that's this vertical line right here. If x equals 1, that's this vertical line right here. So what we're doing is we're finding the shaded region between those two vertical lines. So what we're doing is the area between these two curves is kind of like on the outsides, where in the last example it was between f and g because they met at 2 points. These two curves don't intersect. So sometimes they might give you two curves and you have to find the points of intersection and find the area between them. Other times they're going to pre-bound them for you. So what that means is we're finding the integral from 0 to 1, where it's the top curve. So in this case, the top curve is in red. So it's x squared plus 2 minus the bottom curve, which is negative x. So you'll see me, I kind of bracket these problems in because truly you need to bracket this stating that you're dxing this as all one function from 0 to 1. So algebraically, this is a quadratic, which means if I integrate it, I'm going to get a cubic. But I don't really care what my function is so much because I'm getting a definite answer. But when you do this, the antiderivative of x squared is 1/3 x cubed. The antiderivative of 2 is 2x. This minus a minus is kind of like a plus x. So the antiderivative of x is 1/2 x squared. And I'm evaluating from 1 to 0. What's nice about the 0 is when I subtract, I'm subtracting 0. When I plug in 1, I kind of just take all the coefficients. So it's 1/3 plus 2 plus 1/2 minus 0. Which is 17/6. So that orange region is 17/6. That's the area between those two curves. Okay. Find the area of the shaded region analytically. So again, that just means that we're going to find it using integrals. Now, what do you notice when you look at this graph here? Yeah, some of it's in the positive, some of it's in the negative. So that's going to kind of change a little bit. What else do you notice kind of about it? If I looked at the picture as a whole, yeah, it's a trig function, but I know, I'm trying to get you to, it does kind of look like a bat. But if you look at the region on the left and you look at the region on the right, yeah, would you not say that this side and that side are perfectly even? So what you want to do if you see problems like that is instead of finding it from negative 5/3 to 5/3, I can do it from 0 to 5/3 and double it. And what makes something like that nicer is a lot of times plugging in 0 is nicer than plugging in a negative 5/3 or something of that. So if you see symmetry, especially occurring at 0, then use that idea and double the one region versus finding the entire region. So what I'm saying is that the integral from negative 5/3 to 5/3 will be equal to 2 times the integral from 0 to 5/3 for these two functions. So what would be my top and what would be my bottom? Is going to be my, yep. And then the bottom, yeah, the negative 4 sine squared t. So let's do our integral. It's 2 from 0 to
Julia Stein and Seth Alderson, please come to the office. Julia Stein and Seth Alderson, please come to the office.
Did you pull out the 1/2 and negative 4, or is that not allowed?
You can, but you gotta make sure you pull them out fairly. So like, because 1/2 isn't the same as 4, if you pulled out 1/2, you can only pull out like half of it. Like you'd only be pulling out the 2. So it would be the 1/2 secant squared t minus a minus, which becomes a 4 sine squared t. And all of this is dt. So your question, though, kind of leads into a different thought for me. These two functions are being summed together.
Yeah.
Well, we have that rule that if I'm summing two parts together, I can integrate them separately. So I could rewrite this so that if I did take out the 1/2 and the 2, I'd get the integral of 0 to 5/3 of secant squared t dt plus, I could do the 2 and the 4 together now to get 8 0 to 5/3 sine squared t dt. Okay? So what's the antiderivative of secant squared t? Cool. What's the antiderivative of sine squared t? Yeah, I would want to use a u, but can I do a u with a sine squared? Because if I do u, what's my du? Cosine. So do I have a cosine? No. So this is one of those icky trig rules where you have to like get rid of sine squared. Okay, so 1 minus cosine squared still doesn't help though, because then I now have a cosine squared. So there's another one.
1 over cosecant squared?
Still one help me.
There's so many of those rules, I
I
don't know.
So there's our gross one, which is negative 1/2 cosine 2 theta, and then minus 1.
What is that from?
Right. She should have taught you.
What is that?
It's on like, it's,
What is that rule though? Which
so,
one of
you want to
those?
see like how it came from?
Like,
Like, the idea is that,
is that like a double angle?
yes. The idea is that cosine 2 theta is truly 1 minus 2 sine squared theta.
So, add one double.
Yes. So you subtract over the 1. And then divide by your negative 2.
Wow.
So really though, this is what you're subbing in, because the negative 2 is going to come out with the 8.
Well, does it stay as theta or do you keep
Oh, dt.
Okay. So,
Take the 8 and divide by that negative 2. And we're going to pull out the constant. So it'll turn into negative 4.
hey, it's just like it was before, right?
Is 5/3. And then it's cosine 2t minus 1 dt. So again, secant squared t becomes tan t. And you apply 5/3 to 0. Minus 4. There's I gotta be careful. Cosine of 2t.
5 by 2.
Yeah, you have to make sure you redivide by 2. Because it'd be like cosine of u and the du's. But again, I taught you that there's a value on the t. Just divide by it. So antiderivative of cosine is sine. So you get sine 2t all over 2. And antiderivative of negative 1 would be all of that gets evaluated from 5/3 to 0. Yes. So, tangent of 5/3.
Right where you
Tangent of 0. 4 divided by 2 is 2. So you get negative 2. Sine of 2 5/3. So again, you gotta kind of go into quadrant 2. Well, root 3 over 2.
Yeah, oh, sorry.
Yeah, sine. So it'd be root 3 over 2, but then because you're over there,
We got to tell you what he said today about
okay? And then t is 0, or well, t of 5/3, so we'll forget that one. So remember, it's negative 4 distributed to a negative 5/3. So it's positive 4 5/3. Sine of 0 times 0 times 4 zeros out. 0 zeros out. So look what happens to my 2's. Okay, cancel. Look what happens to the root 3's.
Whoa! You canceled.
So the area of the region.
4 pi, all that for that. I still don't understand.
That's a double angle identity.
Oh, yeah. We never really touched on those.
terrible.
I mean, like, we had it on a sheet.
Yeah.
Like, we never really dealt with it.
Okay. Those are like the only ones, like the double angle and like the Pythagorean ones that you really need to know.
It's awful.
Kind of.
The other ones I remember were like science for it. What?
Alright, let's look at one last little example. It is not.
Yeah, I wrote in there.
So it says find the area of the region bounded by y equals x squared and x plus y equals 2. So what you have to do is you have to rearrange the terms to be in terms of y equals. So I have to rewrite this.
Is that a 1 next to that?
I screenshotted it from Microsoft Word and brought it in, so it's just like a box. So this is x equal, or subtracting your x, you get y equals negative x plus 2. So if we have y equals x squared, that's 0, 0, 1, 1, 2, 4. If I graph my other curve, all I need. I do. If I graph the second line, I have y equals negative x plus 2, so it goes through y-intercept 0, 2.
Okay, well, what about the other side? Of the parabola, that line keeps going in the area over there. Well, I can't help this area. Oh, yeah, that's a good thing.
We're finding this little space.
But he's saying that how do you know that, like,
Why?
because if you keep going to the left, that negative x plus 2 is going to intersect on the other side too.
I'm wondering, so this is like,
And you just got done telling us we're not doing this with respect to the x-axis.
Why is
So
it
the other side would make more sense.
Why is it the area that they intersect with? Like, you know what I mean?
like between the two.
That's what you mean.
Why do you
Like you're saying this.
Because now we're doing it with
Yeah.
the x-axis again.
It's, well, no, it's from your textbook, and I just wonder if I didn't take all the words out. On the area of the region, like, is squared.
Just skip it.
No, it's fine. We'll just do it. Just say bounded. Just add. No. Well, it's fine. You can say that. Or I was going to say bounded by.
What this lesson is not. Okay.
It can still be bounded by it.
So from 0 to 2.
We wrote it from 0 to 2.
So 0 to 2. What's going to be the top one?
That's like why I picked this one. So that's where I said in the definition, it says where f of x is always greater than g of x. So in this example, for part of it. So do you see here how the top curve switches?
Yeah.
So what's happening
no,
is
no.
from 0 to 1,
Yeah,
it's bounded by x squared and the x-axis. From 1 to 2, it's bounded by negative x plus 2 and the x-axis. So I picked this, I picked that on purpose to show you that sometimes the top and bottom curves do change. Or if we're finding the region bounded by these two curves and the x-axis, which I think is, it just needed that word here, bounded by the x-axis, because it was the top to the bottom, top to the bottom. The bottom is the x-axis. The top is changing. So from 0 to 1, the top is x squared. And then the bottom, well, the x-axis is 0, so it'd be like minus 0. So that's why we've never really included it before. Plus 1 to 2, bounded by the negative x plus 2. So the area of this red region are these two sums together, which is 1/3 x cubed 1 to 0 plus negative 1/2 x squared plus 2x from 2 to 1.
If we wouldn't have said bounded by the x-axis, would we be finding the area that where they intersect?
As I said, I just needed that word.
So when it says that, that's indicating the x-axis is the following function.
It could even say bounded by the line y equals 2. And what we're going to do is we can actually flip these and integrate right to left versus top to bottom. And that's what we're moving to tomorrow.
Right to left.
Right to left. Or left to right. Yes. We can change and we can integrate with dy's instead of dx's.
Okay, anyways, let's just focus on this for now.
See it, 1/3, right? Minus 0. Plus 2 squared, which is 4. 4 divided by 2 is 2, but it's negative. Plus 2 times 2, which is 4. Minus negative 1/2 plus 2. You lost some signs, didn't you? So your negative distributes, so that becomes a positive, this becomes a negative. Negative 2, and 4 cancel out, so you get 1/3 plus 1/2, which is 5/6. We have half an hour of time in class to get those problems done.